Swayam Prabha. Digital India. Educated India.
Good morning. Today I'll continue the discussion on cascade flow. The contents of the lectures are the effect of viscous flow on cascades. So I'll discuss both the compressor and turbine cascades here. In reality, the flow is viscous, forming boundary layer over the blade surface and wake behind the blade. Thus, the viscous flow is the cause of drag, which in turn affects the lift. Now, what will be the effect of viscous flow? There will be decrease of total pressure between inlet and at a section well downstream of cascade as the fluid passes through the blades. Now, why this pressure loss appears? This is because of frictional effect on the blade forming boundary layer and losses due to mixings of wake behind the blade. Thus, there is a two component of pressure loss. One because of skin friction on the blade surface, and the second due to the mixing locks behind the blade. What I have stated earlier that I have explained through a schematic of compressor cascades. So I have indicated the flow passing through a compressor cascades, and this is the axial direction. I have indicated here S be the pitch of the cascade and C is the chord. P01 total pressure at inlet and P02 be the total pressure at far downstream of cascade. Now, incoming flow is uniform, having a velocity of C1 that makes an angle alpha 1 with the axial direction. Now, because of viscous effect, now the boundary layer will appear on the blade surface. I have indicated here the formation of boundary layer. And due to the formation of boundary layer on the blade surface, immediate downstream of the blade, the wake will appear with a velocity deficit. So the velocity profile will not be uniform. I have illustrated here a high velocity deficit. Now, at a section far downstreams, this wake will mix and we may get a section where the flow will be uniform here. Again, having a velocity C2 where C2 is less than C1 being a compressor, and alpha 2 will be less than alpha 1 at a section which is far downstream where the flow again becoming uniform, right? As I have indicated here, the pressure be P02. What I have explained here is the formation of boundary layer and wake behind the blade has been explained here by another figure so that you can appreciate. I have indicated the shaded region on the blade surface illustrating the viscous layer, the formation of boundary layer. And if I zoom the section here, say suppose this is the surface, curved surface, and if you zoom near the surface, you will find the boundary layer forming on the surface. So we'll get a velocity profile as I have indicated here. Trust you would appreciate now, because of viscous flow, boundary layer will develop on the surface. And this boundary layer will lead to wake behind the blade. You can concentrate a section immediately downstream where you will realize that velocity profile having a high velocity deficit. Thus, it is a completely non-uniform velocity profile. And far downstream, this high deficit will relax, appearing towards a uniform profile. The shaded region behind the blade illustrates the channel of wake and where the viscous effect is predominant due to the non-uniform velocity gradient. Thus, this figure illustrates the boundary layer formation and the travel and mixing of wakes behind the blade. Now note that since the flow is uniform far downstream of blade, I can say that the kinematics of flow and thus the dynamic pressure remains unchanged between upstream and at a section far downstream of blades. Thus, the loss in total pressure is same as that of static pressure. So I can define the total pressure loss omega tilde equal to P01 minus P02, where P01 is total pressure at inlet and P02 is the total pressure at far downstream where the flow becomes uniform. Now this total pressure omega tilde has two components. One component is because of frictional loss on the blade surface that occur because of the formation of boundary layer. And the second part, as I have told earlier, the mixing of wake behind the blade. Now I'll discuss on compressor cascade and would derive here the analytical expression of actual lift coefficient because of viscous effect. I have indicated here the sketch of a compressor cascade where the flow will be deflected through the blade, and as it will pass through the blade, it will be decelerated, and therefore the pressure at exit will be higher than that of the inlet. However, I have indicated here total pressure at inlet is P01 and that at exit is P02. Now because of viscous effect, there will be decrease of total pressure, and the decrease of total pressure omega tilde is given as P01 minus P02. Now if we consider S is the pitch of the blade, pitch of the cascade, right, and C be the chord. Furthermore, I have indicated for the cascade, Cm be the vectorial mean velocity, and alpha m is the angle that Cm makes with the z-axis. Here z is the axial direction. Thus, there will be a force that will act in the axial direction per unit width of the blade, that would be equal to S into omega tilde. I have indicated here. Now, as for the definition of lift, lift is perpendicular to Cm, as I have shown, and the drag is parallel to vectorial mean velocity. Now this omega S into omega tilde, which is the axial force because of total pressure loss, that will have two components. One will act parallel to Cm and one will be perpendicular to Cm, right? The component which is parallel to Cm will define the drag, and the component which is parallel to the Cm will define as drag, and the component which is perpendicular to Cm, that will decrease the lift, rather theoretical lift, that will decrease the theoretical lift. So here I have written drag is equal to S into omega tilde into cos alpha m, and the effective lift as rho Cm into gamma. This is the theoretical lift, rho Cm into gamma, minus S into omega tilde into sin alpha m. Look, this S into omega tilde into sin alpha m, that is coming here because of viscous effect. Thus, for a compressor cascade, the actual lift will be reduced due to viscous effect or because of drag, which is expressed as L is equal to rho Cm into gamma minus S into omega tilde into sin alpha m. And drag here is S into omega tilde into cos alpha m. Thus, substituting the value of omega S, the actual lift would be rho Cm into gamma minus d into tan alpha m. Therefore, we can conclude stating that the actual lift coefficient for a compressor, considering the viscous effect, would be Cl is equal to twice S by C tan alpha 1 minus tan alpha 2 cos alpha m minus Cd into tan alpha m, where the coefficient of drag Cd can be defined as d divided by half rho Cm squared into C. C is the chord. Now I'll go to the turbine cascades. What happened to a turbine cascade is that the drag contributes to the work output. Therefore, the drag here can be considered as useful. Thus, what would be effect? The actual lift here would be more than the theoretical lift because of useful drag for a turbine cascades. Now I have express here the analytical expression for effective lift for a turbine caskets. So here is the sketches for a turbine casket, and as before, this is the axial direction. P01 total pressure at inlet, and P02 is the total pressure at exit of the turbine. Flow will turn through the turbine, right? And obviously here alpha 2 will be greater than alpha 1. C2 exit velocity will be higher than C1 as the flow will accelerate in a turbine casket. I have indicated as before Cm, vectorial mean velocity that makes an angle alpha m with the z-axis. S be the pitch of the blade. So as before, there will be an axial force per unit width of the blade, that is S into omega tilde. It will walk vertically down as shown in the picture. Now S into omega will have two components. One is parallel to Cm, another is perpendicular to Cm. The component which is parallel to Cm will create the drag, and thus the drag is given by S into omega tilde into cos alpha m. And the perpendicular component of S into omega tilde will increase the lift. So actual lift here would be rho Cm into gamma plus S into omega tilde into sine alpha m. So look here, because of viscous effect, the lift has increased in case of a turbine casket. Thus, the actual lift coefficient for a turbine casket can be expressed as CL equal to twice S by C within bracket tan alpha 2 minus tan alpha 1 into cos alpha m plus CD into tan alpha m. Look here, the component of drag has been added to the theoretical lift. Thus, we can conclude for a turbine casket, drag is a useful component for work output and it increases the lift. Thank you for listening.